Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Mubarak bin Muhammad Bakri, and today I'm going to present experiment 4, minor losses in pipe. First of all, abstract. This experiment of flow measurement is conducted and is related to the study of fluid mechanics. In this experiment, the objective is to study the time taken for volume of water to be displaced by using a pressure measurement test bench. The time taken will be measured between what type of pipe component is used, such as fitting with a sudden enlargement or contraction, 90 bands, 45 bands, and Y-type fitting. From the experiment, we found out that 90 angle pipe is the pipe component with the highest loss coefficient compared to other pipe component that we use. Meanwhile, sudden contraction is the pipe component with the least loss coefficient among all the pipe component that has been used in this experiment. Next is objective. The objective of the experiment is to determine the loss coefficient and minor loss in pipe component or fitting for different water flow rates, pipe diameter, and pipe bend. Next is introduction. The head losses of pipeline are caused by major loss and minor loss of pipe. In the experiment, we are focusing on minor loss. Minor losses in pipelines are due to pipe fitting, changes in the flow direction, and changes in the flow area. Due to complexity of piping system and the number of fittings that are used, the head loss coefficient is empirically derived as quick means of calculating the minor head losses. During the experiment of minor loss in pipe, the key is to find loss coefficient caused by such reason that will increase the friction in the pipe. These friction factors are water flow rates, pipe diameter, and the bending angle of pipes. After the experiment, the relationship between this factor and loss coefficient is found. In conclusion, the factor will affect loss coefficient and total head losses in the pipe.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our group. So I will present about my part, which is theory in minor losses in pipes. So minor losses in pipes come from changes and components in the pipe system. This is different from major losses because those come from friction in pipes over long spans. If the pipe is long enough, the minor losses can usually be neglected as they are much smaller than the major losses. Even though they are termed minor, the losses can be greater than the major losses. For example, when a valve is almost closed, the loss can be almost infinite, or when there is a short pipe with many bends in it. There are three types of forces that contribute to the total head in a pipe, which are elevation head, pressure head, and velocity head. Minor losses are directly related to the velocity head of a pipe, meaning that the higher the velocity head there is, the greater the losses will be. Units for minor losses are in length, such as feet or meters, the same as any of the three types of head. A separate head loss coefficient, which is K, can be determined for every element leading to minor losses. K is a dimensionless parameter to help determine head loss. The coefficient is then multiplied by the velocity head to get the head loss as shown below. Okay, this is equation 1. So F is Darcy friction factor, V is average flow velocity, L is pipe length, G is acceleration due to gravity, D is pipe inside diameter. So the second equation, RE is Reynolds number based on inside diameter, then absolute roughness, then shear stress at the pipe wall, and the last one is rho, which is fluid density. Okay, for the third equation, for the laminar flow, the exact theory for the friction factor results in an expression which is independent of relative roughness. So this is the equation, the third equation. Next, for fully turbulent flow, an adequate expression for friction factor is more difficult to determine from theory. An accepted practice is to determine the friction factor from the Modi chart for pipe friction. The Modi chart was developed from the Colebrook equation, an interpolation formula based on experimental data, while the Colebrook equation was used to develop the Modi chart. It is cumbersome to use. An alternate explicit formula is attributed to Helen, which is the fourth equation, the turbulent flow equation. Okay, afterwards, in addition to screen friction losses in pipe, there are additional minor losses due to fittings, baths, gradual and sudden expansion or contraction, and entrance and exit effects. Since the flow pattern in baths and fittings is quite complex and varies from one manufacturer to another, there is no accepted theoretical means of determining these minor losses. The losses are usually measured experimentally and correlated with the pipe flow parameters. The measured minor loss is typically expressed as a ratio of the head loss to the fitting or bath to the velocity head of the attached piping system. So the resulting ratio is called the loss coefficient K for the fitting or bath. So this is the equation. Okay, and the last one, thus the minor losses may also be expressed in terms of the velocity head once the loss coefficient has been determined. So this is the last equation for minor head losses. Okay, we go through to the apparatus. So this is the apparatus for experiment minor head losses. So in figure 1, we have drainage tray, pressure gauge, tachometer, flow measuring bucket, load hanger, main reservoir and pump. So this is that is the Cousins P6112 hydraulic bench fit with variable speed unit. So in the figure 2, which we have pipe bands and fittings apparatus. So we have globe bath, gate bath, short radius elbow, long radius elbow, manometer tapping, pipe union, manometer tubes. So that is the apparatus for this experiment. Okay, we go through to methodology. So the first one is barometric pressure and the water temperature were determined. Then both the globe valve and the gate valve on the test panel were open. And next, the pump inlet valve was open to its fully open position. This valve should remain fully open at all times. Number 5, the valve on the instrument panel, which main control valve, was open. This valve should be used to control the flow rate during the experiment. Number 6, the pump was started. The speed controller and the main control valve were used to establish a steady flow. All air bubbles from the system was removed. Number 7, select 2 of fittings across which pressure drop measurements are to be made. This may already be selected by the instructor. Connect manometer tapping point immediately preceding each fitting under test to the left of each pair of manometers using the flexible tubing. Number 8, manometer tapping points were connected immediately after each fitting under test to the right hand tube of each pair of manometers using the flexible tubing. All air from both sections of flexible tubing was removed. Number 9, the flow rate was observed using either the rotometer if it is placed in series with the pipe system, or the bucket or stopwatch method. See flow rate measurement section. Number 10, the stop cocks of the manometer tappings was open that been used. Number 11, when the level in the manometers are steady, the difference in water levels between the two tubes of the manometers were not. Number 12, steps 9 to 11 for various values of flow rate were repeated. The flow rate may be varied using the speed controller of the pump. Okay, the last one, the stopcocks on the manometer tappings were closed.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan bin Muatta, and I'm going to talk about the results and the discussion. For the results, there are 3 tables. Table 1 for sudden enlargement and sudden contraction. Table 2 is for elbows and elbows and bends, while for table 3 is for pipe branches. And as you can see in table 1, we are given the volume, the time, the H1 and the H2, and then we are to calculate the actual flow rate, which is from the ratio of volume water collected over the time in seconds, and we find the delta H, which is H1 minus H2, and then we do this calculation for each table. For the discussion part 1, we are asked to calculate the minor head loss, HLM, and the loss coefficient, KL value, for each of the pipe components and fittings. For the sudden enlargement and the sudden contraction, first we can find the V, the velocity, which is from the equation V equals to 4Q over pi di squared. And then from the V that we found, we can find the Reynolds number, which is Reynolds number equals to V di over the kinematic viscosity. And the kinematic viscosity, we assume that the temperature of the flowing water is 7.095 times 10 to the power of -7 meters squared per second. And then from the Reynolds number, we use the Blossier's equation, which is to find F, the friction factor, which is F equals to 0.316 over the square of the root to the power of 4 of the RE. And then we can find the KL. For sudden enlargement and sudden contraction, the KL has its own equation, while for the pipe branches and the pipe angles and the pipe bends, they have their own coefficient of KL. For KL, for sudden enlargement, it is KL equals to 1 minus AI1 over AI2 squared. And while for sudden contraction, it is the other way around, which is 1 over AI2 over AI1 squared. And then that's how we are going to find HLM, which is equals to KLV squared over 2G. And then we can calculate the HL, which is the head loss, with the equation FL over DI times V squared over 2G. And then the total head loss, which is the summation of HLM and HL. And we do this calculation for all the table, for the pipes, for the branches, pipe branches, for the pipe angles and pipe bends. For discussion part 2, we are asked to discuss the effects of different water flow rates, pipe diameters, and pipe bends on the value of loss coefficient KL. And as we know, different elements that can have an effect on the value of loss coefficient. For example, the water flow rates, pipe diameters, and pipe bends. And in terms of water flow rate, the higher the water flow rate, the lower the value of coefficient KL. We know this because of the equation KL equals to 2G HLM over V squared. And then we can see that KL is actually inversely proportional to the V, the velocity, or the water flow rate. So as the water flow rate increases, the KL value will decrease. While for pipe diameter, the pipe diameter, as it decreases, the loss coefficient KL will increase. From the equation given to calculate the head losses of the pipe, HLT is equals to FLV squared over 2G plus KLV squared over 2G. And we knew that the head losses is proportional to the loss coefficient KL. And then to calculate F, we use the Blossier's equation, which is F equals to 0.316 over the root of 4 of Reynolds number. And the Reynolds number is equals to rho VD. And then the pipe diameter, they influence the loss coefficient. And then from the equation shown above, we knew that the loss coefficient is inversely proportional to the diameter of the pipe. And the bigger the pipe diameter is, the lower the coefficient, the loss coefficient KL. For the effects of bends on pipes, we know that from the calculation and tables in the result, we know that as the bending angle increases, the loss coefficient increases. as you can see from the table, for 45 degrees angle, it has the lowest KL value compared to 90 degrees bend and 90 degrees angle pipes. So the bigger the angle, the higher the loss coefficient KL. For discussion part 3, we are asked to briefly discuss on factors contributing to errors or inaccuracy in experimental data, and also the possible recommendations to improve the existing results. There are some factors that will cause inaccuracy of the results, and for example, systematic errors. Systematic errors, there are many reasons for it to occur, such as like the weather or the apparatus being used. And in order for us to overcome the error, we can carry out the experiment indoor or in the lab. Also, we need to make sure that the apparatus is all in a good condition, then we can do the experiment smoothly. Well, for other factors, the other factor is parallax error, and the parallax error is the error when reading the measurement. And to overcome this error, we just need to make sure our eyes, they are perpendicular to the reading of the measurement when the experiment is carried out. Thus, we will get more accurate results. For the conclusion, we can conclude that we know that the major head loss and the minor head loss make up for the total head loss in a pipe. And from this experiment, different water flow rates, pipe diameters, and pipe bends, they can have an effect on the loss coefficient. And this loss coefficient, they contribute to the value of the minor head loss. Even though the minor head loss is not a major part of the total head loss, it is still important, as these losses, they represent the additional energy dissipation in the flow.